So, please help yourself. Now we have a very important talk of a very important person from MIT.
Not a very important
A superstar Justin Salomon will talk about geometric deploying and related things. I mean that nowadays geometry data is very important because of all those sliders and other sensors. And actually, the whole new world of new machine learning topics are there to process this type of data. And so, Justin will tell us about some things related to this stuff.
Okay, well, thank you for the energetic introduction. Unfortunately, I can't quite match that today, actually, and I'm like very confused where to look right now. I was diagnosed with a vocal cord issue just last week, so if it's a little bit of a squeaky lecture or you can't hear anything, I apologize. So feel free to stop me if you have questions you can't hear or what have you. Right, so to give a little bit of background, I'm coming here from MIT in Boston. My research group actually studies a lot of problems in geometry and machine learning. The main themes that we study are optimal transport and deep learning on certain geometric representations, which are being covered at this event by this morning's talks and what you'll hear tomorrow morning, respectively, which left me to cover some other topics in geometry. So I'm going to have 3 different talks here at the Machine Learning Summer School to give you guys a flavor of some other places where geometry appears in the machine learning world. So today, we'll talk a bit about embedding problems. So the basic idea of embedding is that you have, in machine learning, it's very typical to have extremely high-dimensional data, right? You collect all kinds of information, and you get these big clouds of data points. And of course, there's a problem with dimensions that are larger than 3, which is that we can't actually look at them, right? And so you have extremely high dimensional data, and visualizing this data, navigating it, and so on can be extremely difficult because the dimensionality is too large. And so there's a whole class of different types of machinery that's intended for tasks called embedding tasks, where I want to take high-dimensional or structured types of data and embed it in a lower dimensional or simpler space while preserving the structure that's there. So you might be wondering why there's an image of dessert on the slide here. Of course, the most typical data set, and one that we'll see later on in today's talk for testing embedding algorithms, is something called the Swiss roll data set, and it comes from making food like that. In addition to being delicious, the main thing to take away about the Swiss roll is that, of course, there's a 2-dimensional structure that's embedded inside of a 3-dimensional object. Right? So in particular, the way that you bake one of these objects is you make this very thin slice of chocolate cake, and then you fill it with some cream, and you roll it up. And there's a question here, which is, of course, this is a 3D piece of cake. It's sitting in 3-dimensional space, and it looks like a cylinder. But intrinsically, there's 2-dimensional structure hiding inside of it. Right? And so the question that we'll try to answer today when we talk about embedding algorithms is, can we expose that structure and leverage it for interesting inference, visualization, and other kinds of procedures? So that's our basic setup here. There are many different ways to describe the embedding problem. I come from the computer graphics world, so I'm morally obligated to show you the Stanford bunny at least one time in any given talk. But one way to kind of understand embedding problems is as an inverse sort of a problem, right? So a very typical thing that we do in geometry is compute distances between points. Right? So here we have this 3-dimensional bunny here, and there are many different notions of distance, right? There's distance in 3D. There's also something called geodesic distance, which is like the shortest path between 2 points if you are constrained to move along the surface. And so this is what we might call a forward problem, right? Given a piece of geometry, the forward problem is computing distances between points. Then, the inverse problem, and the one that we'll speak about quite a bit today, is if you're given a set of distance values, can you go backward from that to an embedding of your data? Right, so obviously, in this particular case, with the bunny, it's probably not terribly clear why it's practical, but we'll see that there's many cases and many different scenarios where embedding is really a useful tool. Now, when we talk about embedding problems, we need to establish a little bit of vocabulary to get started here. One question and one set of terms that are very typical in the geometry world is to distinguish between intrinsic and extrinsic geometry. So let's go back to our Swiss roll example here. The Swiss roll is a great example of something that's simultaneously 2-dimensional and 3-dimensional. right? Obviously, as a cylinder, piece of geometry, it's sitting in 3D, right? If I do PCA on the set of points on this round object here, what I'll get are 3 different eigenvalues, all of which are far from 0. But at the same time, hiding inside of here is a 2-dimensional structure, right? There's the kind of spiral hiding inside of the cake, and then there's a second dimension which is moving along the side of the cylinder. And so when we talk about embedding algorithms, we'll find that both finding extrinsic and intrinsic geometry is interesting, right? Like it could be that even the extrinsic geometry of this cylinder is hiding in 20-dimensional space, or we might want to go to the additional work of taking that cylinder and unrolling it into a 2-dimensional object, right? And depending on your task, both of these things can be important. Now there's a reasonable question, which is that you may have encountered algorithms for this kind of thing, but with many different names, and indeed that's the case. This is a very sort of natural idea in math and computation, and different names of tasks that are similar, if not identical, to embedding include dimensionality reduction, parametrization, manifold learning, and so on. These, in my mind, are all sort of similar, if not identical tasks in machine learning, where the basic point here is that there's some low-dimensional object hiding in high-dimensional space, and your job is to try and expose that. Okay, so before we go crazy with totally complicated algorithms and so on, of course, the first question we should answer is, why bother? Like, what sort of benefits do embedding tools actually give us, is the first question we should answer. And there's many different reasons for that. So, in fact, just during the exercise that you guys just completed, right, one of the very first things that you did after you computed transport distance was to find an MDS embedding. And that's a very typical thing to do, right, which is you have high-dimensional objects, you compute the distances between them, and then you try to embed them in a plane so that you can visualize your data in a fashion that tries to preserve the relationships between the different points. When I say relationship here, it's very straightforward. I mean, like, nearby points in the high-dimensional space get mapped to nearby points in the plane. So for instance, here you see a t-SNE embedding of the MNIST digits. You can see that whatever technique these folks used ended up putting all the sort of similar digits clustered together, which is pretty typical looking diagram that you'll see in successful clustering methods of machine learning. But embedding also has a lot of other advantages to it. So for instance, sometimes it can help you expose some latent structure. So there's a very famous technique that was proposed a couple years ago called word-to-vec. This is a little bit crazy when I originally saw it, where they take every word in the English dictionary, I assume somebody has tried to reproduce this for Russian, and then embed it into Euclidean space. Like, so every word gets mapped to a vector in Rn for some large n. And the idea is that in my embedding, I want nearby points in Euclidean space to maybe correspond to similar words, where in this case, they measured that by some kind of co-occurrence. Like if you're nearby in a sentence, then maybe you should be embedded closer by. And one of the really magic conclusions that they reached in this work, and this was largely empirical, was that not only did you get embeddings that preserve structure in terms of like adjectives or similar words get mapped to a similar part of space, but actually that you can do arithmetic on this embedding and it's sort of sensible. Like, so for instance, if you have, London minus bridge plus tower, maybe you get Paris back. This is a really surprising empirical observation hiding inside of this work that I think still lacks a little bit of explanation. There's some thinking that needs to be done here. And then finally, one additional reason why you might think about embedding is purely algorithmic in nature, right? There's a lot of algorithms where essentially the algorithm scales with the dimensionality of your data, right? So for instance, in Marco's talk earlier today, we saw that certain transport problems degrade or become more difficult to solve as the dimension increases. Or here's an even simpler one. Let's say that I have n points in d-dimensional space, and I just want to find like my closest neighbor. Well, how do I do that? I iterate over all the n points, and I compute the distance to each one, which of course means I have to iterate over all the d dimensions. There are faster algorithms out there, things like KD trees, but even that simple algorithm already you can see scales with dimension. And so if you can embed your data into a lower dimensional space, sometimes your machine learning procedure can be faster without a significant degradation in the quality of the result. In fact, sometimes it can improve. That maybe the high dimensional structure is basically just noise. And then finally, in case I haven't convinced you enough that embedding is an important problem, any self-respecting machine learning talk should, I guess, contain one neural network these days. And indeed, if you look at the layers of your neural network, What are they? Well, they're nothing more than embeddings of your data into different spaces. In this case, Euclidean space, right? So like, if I look at the last layer of my neural network, what have I done? I've mapped a data point or an image or what have you to a set of descriptors for that image, right? One per output of my network. And if you kind of squint at that, that's nothing more than an embedding into a space whose dimensionality is equal to the number of nodes on the right-hand side. Now, why does that matter? So we're going to talk a little bit about embedding theory today, which tells you what spaces embed well into what other spaces. So implicitly, what have we done here in our neural network? Well, in this case, we've embedded it into the two-dimensional plane, right? There's two outputs in our network. And so a reasonable question you might ask is, well, what data maps well into that two-dimensional space? And we'll see that there's actually some data for which this embedding might work quite well. There are other types of data for which embedding into any Euclidean space might actually work quite poorly, which could help explain, good or bad performance of your learning procedure in practice. Okay, so to get started today, let's start with sort of a simple task here, which is I give you a big matrix of values. And here the entry ij in my matrix is the distance between point I and point j. And the question is, can I extract an embedding of my data into some space? In other words, can I come up with a set of points so that when I compute the distances between those points, I get back the distances that I have in my input matrix? I should pause here. Does anybody have any questions? Because this talk's going to be awfully boring if you don't get the basic problem set up. It's okay, don't be shy. I'm squeaky and making lots of noise. No? Okay. Fabulous. Yes, but I didn't send them to you. Is Alexi here? Because I know he happens to have access to them. God, I hate this room. I'm sorry. No. I will post them after today's lecture, and for the remaining two, I'll be sure to post them beforehand. Yeah. Thankfully, the slides don't have too much on them, because I get myself confused if there's a lot of text. Okay. So, right, so before we talk about algorithms for embedding, we should answer an even more simple question, which is this always possible? Right? Is it always possible to solve this problem well? And in fact, that turns out to actually be a very tricky question to answer. So, in order to do that, the first thing we should do is define all of our terminology. So the first thing we should define is, what does it mean to be a distance? Right? And of course, there's a pretty simple definition here. A distance is a function from 2 points, x and y, to a value. And it satisfies 4 axioms that I think we all know and love, right? For one thing, distances can't be negative. Distances are 0 if and only if the 2 points are the same. The distance from x to y is the same as the distance from y to x. And then perhaps the only kind of non-trivial one is this last property. This is known as the triangle inequality. And what is this saying intuitively? It's saying that it's always cheaper to travel directly from x to z than to travel from x to y and then from y to z. So this is the basic sort of tenets of what it means to be a distance. And that's a more general thing than distance in Euclidean space. There are certain spaces that don't embed well into Euclidean spaces, but still have distances associated to them. And these actually include many spaces that we care about in machine learning, right? So everything from like shapes, so like on the surfaces and geodesic distances, to distances on a graph or a road network. All of these things satisfy these axioms, but aren't necessarily embeddable very well. So the basic object that we might be after in these embedding problems is a very particular object, and it's called an isometry. So an isometry is a map from one metric space into another that preserves the pairwise distances between points. Right? So maybe my input is a very simple metric space, which is just a matrix of distance values. And then my output is I want, a bunch of points that realize those distances. Right? And in an ideal world, if I've done my problem, I've solved my problem perfectly well, then at the end of the day, I will have extracted an isometry from one set to the other. So now we have all the terminology we need to set up the basic problem here, which is, can we always embed a metric space isometrically into Euclidean space? By the way, when I say Rn, I just mean sets of n numbers. Hopefully this language is familiar. What do we think? How many of us vote yes? Given any matrix of distance values I can embed into Rn for some sufficiently large n. I don't care what it is. I can make it as big as you want. How many of us vote yes? How many of us vote no? How many of us are just like not going to vote no matter what I ask? Yeah, there's a few of you. I see you. Yeah, so the answer is pretty clearly no, because there's some infinite dimensional giant spaces out there. Right? Like the space of functions equipped with the L2 norm is itself a metric space. And it's, I think, pretty intuitive that I can't take an infinite dimensional object and embed it into a finite dimensional space with no distortion. So now let me make our question a little bit more involved. Let's add one more word. Can we always embed a finite metric space isometrically into Rn? So in other words, I have a k by k matrix of distance values. Can I find k points in some Euclidean space so that the pairwise distance between those points realizes the distances that I have in that input matrix? And here I'm happy to make n as big as I want. It doesn't have to equal k. It can equal 10 times k or whatever, k squared. So this is a little bit tricky, right? Because now my argument before about squeezing infinite dimensional spaces doesn't work anymore. So now let's do a survey. So how many of us vote, yes, I can always do this. The next slide's going to have an algorithm on it. It's okay. It's a totally reasonable guess. And who's vote no? So this like adds up to like maybe 2/3 of the room here. Let's try again. How many of us vote yes? Okay, how many of us vote no? So what if I restrict to n? So it turns out that the no's have it. And let me give you a really disappointing example. It consists of 4 points. Here it is. So here I have 4 points, A, B, C, and D. And I've given you the distance values on the screen. And we're going to experiment with this chalkboard business that I'm a little suspicious of. How do I make it into a chalkboard? It has slides on it now. Somebody? Okay, thank you. If it's possible to just leave this as the board, and that's probably best today. Ah, perfect, thanks. Okay, I've never used one of these before. If you guys can't read it, then let me know. Okay, so first of all, the distance from A to D and the distance from B to D is both 1. And the distance from A to B is 2. What does that mean? Well, that means that they have to sit on a straight line, right? So here's, oh, cool. Right, so what do I know? I know that from A to D, it's distance 1. From D to B, it's distance 1. Whoa, 1. And this angle had better be 180 degrees because from A to B is distance 2. Okay, with me so far? So, now from A to C and from B to C, the distance is 2. So in other words, they have an equilateral triangle, right? So I have, I'm not very good at drawing an equilateral triangle, so you're gonna have to believe me. Okay? So far we have an embedding. I've satisfied the first 2 lines of our distances. But now the distance from C to D, so this is C, is 1.5. Is that right? So if I have 1 squared plus 2 squared, do I get 1.5 squared? Some of you are nodding. No, the answer is clearly no. So yeah, so our embedding here, this value has broken the embedding, but you can check that in every triplet here, it satisfies the triangle inequality. So it turns out with spaces larger than 4 points, you cannot necessarily embed into any Euclidean space for any n as large as you want. So that's a little bit of a downer, but it doesn't mean that we're totally hosed. It just means that we can't embed exactly, right? So the next question you should ask is, can I do it approximately? Incidentally, as a point of contrast, if you're a mathematician, you're kind of curious, there are many other spaces out there that are not Euclidean. So one of them is the L infinity norm. So this is like where the length of a vector is equal to the absolute value of its largest element. This is different from like the square root of the sum of the squares. And it turns out you can embed every finite metric space into Rn for large enough n. I'll let you guys work that out at home. I've given you a hint in the slides that I promise I will share after this talk. But in any event, because we've convinced ourselves that typically it's not possible to embed a space isometrically into Rn, well, we're stuck resorting to something else, which is approximation. right? And so what we have to do is measure things like expansion and contraction of our map and try to make these numbers small because that's what's going to define a good embedding. Notice that here, maybe this isn't totally clear. So F is our embedding, so it's a map from one metric space into the other. So when we measure things like expansion and contraction, essentially what we're measuring is like the pair of points where the distance gets distorted in the big direction as much as possible, in the small direction as much as possible, and then multiplying these values together. And there's a very famous theoretical result, which we're not going to prove here today, by Bourgain, I think recently passed away, incidentally, that you can, with sort of very low distortion, map spaces to any LP space, including the Euclidean space, in a way that scales as sort of like the log of the number of points. But anyway, this is mostly a fact of mathematical interest, although if you look at the technique that he uses to prove this fact, you'll see it's actually constructive. The algorithm that he uses is pretty straightforward. It fits in this little box here. Okay. So anyway, that's our basic theoretical setup, and I think it's important to spend a few minutes talking about that just so we know like what our enemy is here before we start cooking up algorithms, right? Like what are the sort of outer bounds of the problem? We don't expect to get a perfect embedding of our data, but we do expect to do reasonably well as the number of points kind of extends it. So now let's talk about some algorithms. We're going to start easy and then we'll step it up. And many of these techniques are fairly straightforward to understand. Some of them a little bit less so, but that's okay. So the first problem that we should start with is sort of a funny chicken and egg problem, which is, let's say that I give you a matrix, and moreover, I tell you that that matrix is the pairwise distances between points in some Euclidean space. So all this stuff from the previous slide just doesn't apply anymore. I know a priori that my matrix has distance values in it that come from Rn. But I forgot where those points were, and now I want to find them again. Yeah, we're starting easy. Then how could I do that? Well, so this is the basic statement of our problem here. Hopefully, by the way, if I have this pairwise distances, if I square it, then I get the pairwise square distances. I think we can all buy that. So as input, I'm given a matrix, Pij, whose entries are the distances between every pair of points. And now I just want to reconstruct the embedding. And it turns out this is a relatively straightforward problem to solve. So how we can do that? Cool. Okay, so what's really hiding inside of this matrix Pij? So if I take a look at my Pij, oops. Okay, well this is, of course, the distance from xi to xj squared. I've never written on a chalkboard that like lags behind. Then one thing we can do is expand the square here. And what do I get? I get, the norm of xi squared minus 2, the dot product between xi and xj, plus the norm of xj squared. Yeah, so it's just by multiplication. And so one thing that you can read off from this expression here is that if I know this matrix Pij, then in effect, just by doing a linear transformation on the elements of P, I know the dot products between every pair of xi and xj. So the matrix of pairwise dot products has a special name. This thing is called the Gram matrix. So if I take all of my data points and I organize them into one giant matrix, so this looks like capital X, where the first column is x1, second column is x2, and so on. Then if I have the matrix of pairwise dot products between every pair of points, there's nothing more than x transpose times x. You guys see that? We can write it down really quick. So, fine. Right, so x transpose times x, of course. So if I take the matrix where every column is a vector, and I transpose it, then every row will be one of my vectors. So it's going to look like x1, x2, that's an x, and so on. And then this is multiplied by x1, and so on. Remember how matrix multiply works, right? The first one goes horizontally, the second one goes vertically. So notice that I get x1 dot product with x1, x1 dot product with x2, and so on. So really hiding inside of that pairwise squared distance matrix is nothing more than the dot product between every pair of points. And this leads to a very simple algorithm. This is called multidimensional scaling. You've probably played with it before in Python. It didn't know that it was 3 lines of code. So in effect, what multidimensional scaling does is it takes as input a pairwise distance matrix and squares every element, so it's got the pairwise squared distances now. Going from that to this gram matrix, in other words, the pairwise dot products, is basically just an application of this, this expression here, just working backward, right? So if I have the pairwise distances, then I can get this thing, and this is like Gij, where G stands for gram. And then from there, okay, if I have a matrix and I have x transpose x, then I can actually recover x by computing the eigenvectors of that matrix, right? And up to rotation. And so that's the final step here. And that gives us our embedding of our data. So this is the simplest embedding algorithm, and it has a very simple guarantee, which is that if my distances originally came from a Euclidean embedding and I just forgot it, then this algorithm will give me my embedding back up to rotation. And of course, that up to rotation actually makes a lot of sense, right? If I rotate a pair of points, does the distance between them change? Well, no, right? So if an algorithm didn't give you the points up to rotation, you should be very suspicious, right? Because somehow something went wrong. Okay, so the multidimensional scaling algorithm is really interesting, but somehow, and people use it a lot in practice. So it's a very simple technique. And what do they do in practice? Well, in practice, you probably don't care about this case that we just proved something about, right? Because if you already knew the embedding, then you don't need to recover it. But you just go through the same procedure on a distance matrix where maybe you don't know that it's embeddable, and you use the embedding anyway, and oftentimes it's close enough, right? And you can actually prove that there's many scenarios where that's an okay approximation. Now, if we really care about the embedding problem, you might ask a simple question, which is, why not just cook up the simplest formulation of this problem and optimize for it directly, right? So let's do that now, and that's going to lead to a technique called stress majorization. Incidentally, many of you have probably seen these things inside of Python, right? This is a very sort of simple tools that show up a lot in data science. So in stress majorization, our input, again, is a matrix D0, where D0 ij is the distance between point I and point j. Right? My job is to find an embedding that realizes those distances. So what are the variables in my problem? Well, in some sense, there are a bunch of points, x1, x2, ... all the way up to xn, right? Just all the positions. And what have I done well in my embedding problem? Well, I've succeeded in computing a good embedding when my input distance, d naught ij, is approximately equal to the distance from xi to xj. Right? In some sense, that's our definition of success for an embedding problem. So if that's true, how should I solve it? Well, I should take these two numbers and subtract them, and I want the difference to be as close to 0 as possible. Right? So how could I do that? Well, I have d naught entry ij. I subtract xi minus xj squared. Oh, not squared. How do I erase? Does this work? Okay. Okay, whatever. Okay. I want this number to be close to 0, but I don't care about its sign, right? So what do? I square, and I sum over all ij. Right? Well, let's see. So if my embedding were perfect, right, then these numbers will be equal, and this whole sum will be equal to 0, yeah? So in general, if I want to write this as an optimization problem, I can minimize over the set of point positions this particular objective function, and it's sort of small exactly in the case that I care about, right? Exactly when the distances between the points resemble the input distance matrix. Does that make sense to everybody? I know the handwriting is a little hard to read here. I'm still getting used to this setup. I should run over here too. Does this make sense? Cool. All right. So now let's see if we can actually do a little bit of computation with this model here and see that it's actually not so difficult to optimize this value. So first of all, for those of you who are sort of familiar with convex optimization, this sort of machinery, Is this a convex problem? Is it least squares? No, it's none of that, right? Because hiding in, yeah, it kind of looks like least squares. There's a square here. But hiding inside of that square, is this, this norm of a vector. And remember, like, what is this thing? It's like got the square root of the sum of a bunch of numbers squared. So this is actually a pretty crazy expression. It's non-convex, it's kind of difficult to work with. So it's surprising that we can formulate a really elegant algorithm for optimizing this thing in practice. Okay, so in order to do that, essentially the only math we're going to do today is to take numbers that are squared and then take the square and expand it. That's our big trick for the day. So let's do that really quick. I'm gonna run out of pages. Okay, so remember that our objective is the sum over ij of the, d naught ij minus the distance from point I to point j. All that squared. Now I'm going to take that squared quantity and expand it. I can get the sum of 3 terms. And we get d naught minus, squared, 2 d naught ij times the distance from xi to xj plus the distance from xi to xj. This is tricky. Okay, squared. It's our big trick today. So advanced mathematics here. Okay, so here's the thing. Optimization problems that are easy to solve often look like least squares. And we're almost there, right? That thing is squared. So the only expression that we don't really know how to cope with is this middle term, right? It's got this annoying norm sitting inside of it that somehow is getting in the way of optimizing efficiently. And so in these algorithms, we're going to do something really sneaky, which is we're going to pretend like it is squared. And here's how we're going to do that. We're going to take just, I keep trying to scroll up, but I think it needs 2 fingers. Good enough. Okay. Okay. Let me erase the weird marks that I made on the screen before. Okay. So, in particular, let's just take this second term here. I'm going to put a star next to it. Well, I can write this second term in a really funny way, which is that I'm going to multiply and divide by this distance here. So I'm going to say that this is the same thing as minus 2 d naught ij divided by the distance between xi, xj, times the distance from xi to xj, well, now squared. So our algorithm for optimizing this objective is going to be really sneaky. Essentially, I'm going to pretend like this value is a constant, then I'm going to optimize, but this value isn't really a constant, so what do I have to do? I have to update that constant and then kind of iterate. Does that make sense? And this is going to be called a majorization minimization scheme. Incidentally, the objective function here comes from this paper. It's recent developments in statistics, where recent means 1977, and it comes from scaling by majorizing a complicated function, or SMACOF, which was kind of an unfortunate piece of terminology, which we are now stuck with forever. Okay, so what have we done so far? So we took our SMACOF objective function, that's in red in the corner here. We expanded this square, and we got 3 different expressions. Here I've chosen to write this in matrix notation, but it's nothing more than the expression that we've already written on the screen. Do you see that? So like the very first one, well, that's actually just a constant in terms of the unknowns, right? So I can, in effect, just ignore this term here, right? Because it's not affected by the x's. The second term is just a very simple least squares term, the kind of thing that we're used to. And then the third one is this funny nonlinear thing. And what I'm going to do is define a matrix B, which just contains this crazy nonlinear function. And as long as I put all the crazy nonlinearities inside of B, then my expression is quadratic. Right? This is kind of a funny way to write it. Okay, so now let's optimize this thing. So we're going to, in order to do that, I'm going to define a function, and then we're going to prove a really clever property about this thing. So that function is this thing called tau. And if you take a look, so I just copied over the expressions from the previous slide to the top of the slide here. What is tau? Well, if I put in x twice, so tau of x comma x, then what I get back is just my objective function here. So this is somehow just splitting apart different parts of this expression into two different variables, x and z. Okay, so that's the definition that we have on the screen. And we're going to prove a really simple lemma, which is that the smallest possible values of tau happen when I put the same matrix into it twice. So in other words, for any matrix z, tau of x comma x is less than or equal to tau of x comma z. It's going to be a convenient property when we want to optimize this thing. So in order to do that, we're going to make use of one identity that you might remember from your pre-calculus class, or whatever the equivalent is in Russia, I have no idea. And that's something called the Cauchy-Schwarz inequality. Okay, and what is Cauchy-Schwarz? It says that if I have two vectors, x and y, and I take their dot product, that's less than or equal to the norm of x, that's an x, times the norm of y. If you can't remember this, remember that the dot product in 3D is like the norm of x times the norm of y times cosine. Remember that cosine's between minus 1 and 1? So that's effectively what's going on here, but cosine only works in 3D. This works in higher dimension. Okay. So, as a corollary of this, let's prove a really funny bound, which is, so first of all, if I take xi, I don't know why the screen is doing that, but this funny symbol means x, it's not an alpha. Xj, and I take the dot product of that with zi minus zj for any x, z, I, and j. Then of course this is upper bounded by xi minus xj, zi minus zj. Well, now we're in business because these are starting to look like quantities that we care about, right? So in particular, let's just reshuffle this. What we can show is that the distance xi minus xj is greater than or equal to this stuff divided by this distance, right? So in other words, that's greater than or equal to, where is it in my notes? Xi minus xj dot product with zi minus zj divided by its norm. Cool? Cool. All right, so now we're going to scroll up very slowly. Okay, good. Let's see. Oh, wait. Nope. Okay, now I won't try to shake the boat too much here. Okay. All right. So essentially, in order to prove the bound that we have, is the constant term going to matter? No. Is the second term in this expression relevant? Well, no, because it only involves x, right? And somehow we're trying to relate x and z. So the only term that really matters in our inequality is this third one here. Cool? So let's write this thing out. So we have minus 2 times the trace of, here it is, x b of x transpose, right? So that would be like in the case where I put x twice into tau. Well, kind of by definition, this is equal to minus 2 times the sum over ij of d naught ij xi minus xj. Like that. Right, and this just comes from actually how we defined b. Remember, we defined it in such a way that this is true. Okay, so now what we can do is apply the inequality that we just proved, right? Because you see that we have an xi minus xj here. That's like the left-hand side of this expression. Remember, there's a minus sign here, so it's actually less than or equal to, minus 2 times the sum over ij of d naught ij xi minus xj dot product zi divided by its norm. And that's just by substituting in the expression that we already have here. Okay? And one thing that we can do is just take this norm of zi minus zj and move it to sit underneath d naught. And what you can check is that's exactly the expression that we have on the right-hand side here. So I think in order to put everybody out of their misery with my trying to write on this screen, we're going to omit a few steps, and I will share a link with you guys to the course notes that I have that go through this proof step by step. But the main observation is this bound from Cauchy-Schwarz, and the rest is just a calculation. Okay? So, why do we do this? Well, we can define a very straightforward algorithm now, where what I'm going to do is I have some estimate x of my embedding, and now I'm going to minimize tau, but I'm only going to minimize it in one of the two arguments. Okay? So, in other words, in every step of my algorithm, I'm going to have the next guess of x, xk plus 1, is the min over all possible x of tau x comma xk. And remember that what is our objective function? What are we trying to minimize? It's like tau of xk comma xk, right? That's the number we want to be small. Okay, so let's double check that we actually got that. So let's call that f of xk plus 1, right? So f is going to be our objective function. Then by definition, that's tau of xk plus 1, xk plus 1, right? Okay, well, now what are we going to do? Well, from the expression, from the inequality that we just proved, this is less than or equal to tau of xk plus 1 xk. That's, remember, because the smallest possible tau in the second argument is gotten by putting the same thing in twice. Now, how did I define xk plus 1? It's the min over all possible x of this expression at the top of the screen here. So what happens if I put in xk in that first argument instead of xk plus 1? Well, this is the min, so it can only get larger. So it's less than or equal to tau of xk. Oh my gosh. Like that. And that's exactly our objective function. So what did I just prove? Well, I showed you if I use this fixed point iteration in yellow at the top of the screen, then in every step of my algorithm, the distortion of my embedding decreases, right? Because the distortion of the embedding at step k plus 1 is upper bounded by the distortion of the embedding at step xk. Isn't that cool? It's a really clever trick. So this is an instance of a pattern that's pretty common in machine learning. It's called a majorization minimization algorithm. And essentially, this is the basic trick. You take all of the hard, annoying stuff that you can't deal with in your optimization problem, and you stick it into a term that you pretend to be constant, then you optimize everything else and you iterate. And often you can prove that this thing converges at least an objective value. So what we have not shown is that the x's themselves converge, and it turns out under certain assumptions you can show that, but it's a little bit trickier. Yep. The nice thing about this technique is minimizing tau over x, where you hold the second argument fixed, you can actually just write down an expression for it, which I have computed on the screen here. So it's really just a formula at the end of the day. And so the nice thing about this algorithm is that it's very clear what its behavior should be, right? Because the objective function is exactly 0 when I've succeeded, as opposed to the MDS algorithm, where it's not so clear what should happen when you don't have an embeddable set of points. And indeed, this is probably one of the more popular techniques for embedding in practice, because again, at the end of the day, the hard part is proving that this algorithm works, but the actual coding for this technique really is just typing in that formula at the bottom of the screen here. Very simple stuff. Okay, and so at the end of the day, so for example, one common application is in graph embedding. So like I have the lengths of the edges of the graph, I put it into the plane. In fact, I thought for fun, I'd point you guys toward one of the speakers tomorrow is Michael Bronstein, and actually one of his research papers shows that you can do this to solve like shape analogy problems, like I have two humans in different poses, and now I have like a human who has a little more of a belly, and he's only in one pose, and I'd like to transfer the other pose to the same 3D model. So these sorts of embedding problems show up all over the place. This algorithm is also sort of a single example out of a very large class of techniques for embedding that are just kind of small perturbations of this technique. So another common one is something called Salmon's mapping method, where essentially the only difference is that the objective is divided by the distance here. So this one cares about small distances, whereas the SMACOF thing cares about large distances, but basically the same algorithm applies here. Nothing changes. And there's another example of a nonlinear embedding technique. There's many out there, and they all have different properties, and it's very difficult to judge the differences between these things. Another very popular one that you may have heard about in practice is something called t-SNE. Just out of curiosity, how many people have played with t-SNE embedding before? Yeah, I think this is a pretty common one. I encourage you to actually read the research paper that describes this algorithm because it's a little bit crazy. And they say as much inside of this paper, it's no secret. But essentially what the t-SNE embedding technique does is it computes a joint probability distribution kind of over the set of points that you have, just with a Gaussian. So you have this very high dimensional set of points, and your task is to embed it in a low dimensional space. But in t-SNE, you're not trying to embed it with low distortion. You're just trying to keep like close stuff close and far stuff far away. But they don't care like how close and how far. That's the difference here. So the way that they propose to do this is you first sort of evaluate a pairwise, a Gaussian in every pair of points. That's this first expression here. And then you embed the points in a lower dimensional space, like the plane. And sort of one way that you might do that is you say, okay, my unknown is the embeddings of the points in the plane, and I'd like that the Gaussians and those distances are similar to the Gaussians in the original embedding. But that's actually not what they do. So what the paper says is, I really like this phrase, that mismatched tails compensate for mismatched dimensionality. I'm not 100% sure what it means, but it sounds great. And essentially what they do is the Gaussian distribution has a very small tail, like it drops off very quickly. And their intuition is that when you embed, you should embed with something with a wider tail. Particularly, they use this heavy-tailed student t distribution. And so what they're doing is they want a student t distribution in the low-dimensional embedding to match a Gaussian distribution in the high-dimensional embedding. I think this is sort of derived heuristically. I wouldn't call this like a very deep technique, except that like it really seems to work extremely well in practice. So the way they optimize this is just with gradient descent. It's very straightforward. One of the tricky things about the t-SNE embedding is that it's a little bit hard to interpret, and it actually can be quite misleading. So like a very typical thing, I guess many of you guys have actually experimented with this, when you run t-SNE, is you get embeddings that look like this, right? So your points have somehow clustered really beautifully. And for data scientists, this is really exciting, right? Because often your task in data science, you're given some unstructured, high-dimensional cloud of data points, and your task is to find interesting structure, right? Interesting clusters in your data. And somehow it looks like, t-SNE is this amazing tool that did exactly that, right? Like in this embedding, it's very clear what the clusters should be. The problem is that t-SNE just really wants to embed stuff with clusters. And often this is actually misleading, that actually in the high-dimensional data, the clusters are very unclear, but just by virtue of the embedding algorithm, rather than by anything that's inside of your data, it ends up looking more clustered than it really is. And so there's a really great website I encourage you guys to go check out, which is called How to Use t-SNE Effectively. And they have lots of really scary counterexamples where you just kind of play with some parameter to the t-SNE algorithm that looks like it shouldn't affect the output, and it totally biases the clusters that you see in your data set, which should scare you. Like that shouldn't happen in an embedding technique. So I would say it's an extremely powerful tool, and often if your data embeds well, but it's high dimensional, then these can be extremely useful and powerful ways to visualize that in a low dimensional space. But you have to be careful. I mean, just the way that this algorithm was constructed, it wants to cluster points together more than perhaps is actually present in your data. And so it's very easy to misinterpret what comes out. Okay. So we still got a little bit of extra time here. So let's talk about some additional tasks. So far, everything that I've told you is an algorithm for sort of finding interesting extrinsic structure in my data. Right? So if I give you a bunch of points that are sitting on that Swiss roll, and I ask you to embed it, well, the kinds of distances that we're computing are like, here's my Swiss roll. If I want the distance from this point to this point, what would I do? Well, in these embedding algorithms, it would be the length of that straight line. But of course, if I care about the intrinsic structure of my data, then I've done something wrong, right? Then really my distance should spiral outward in my Swiss roll. And so let's talk a little bit about techniques that try to expose that intrinsic structure. And this kind of structure appears all over the place, right? So we've already seen it inside of this thing. There's a very famous theorem, right, which is the Whitney embedding theorem or the Nash embedding theorem. It says that any n-dimensional object, or object here is Riemannian and manifold, can actually be embedded into Euclidean space as long as the dimension is 2n. But the embeddings can be pretty crazy. So like, here's a flat torus embedded into 3D, and you need these like kind of fractal patterns to make it work out correctly. So this is probably not a very practical thing. But there are many practical techniques out there that are intended to expose intrinsic structure, and they tend to be quite straightforward. So here's a technique called ISOMAP. So out of curiosity, how many of you have played with ISOMAP or LLE? Many of you. So yeah, this is another sort of common technique in data science, where essentially all we do is it's just like a little bit of a hack on top of MDS, or one of these algorithms we've already talked about, where I have an algorithm where once I have a distance matrix, I know how to embed it into Euclidean space. And there's a question that we haven't really answered yet, which is which distance matrix should I use? Right? So far, if I just compute Euclidean distances between points in my original embedding, then what I'll get is some extrinsic technique. A different thing that I could do is construct a k-nearest neighbor graph on my data. So I take every data point, and I just find the k closest data points inside of my data set. And so you can see I've done that on the Swiss roll data, right? And what I get as output, every point is just connected to nearby stuff in this thing. So in other words, there's no edge, for example, from the inside of the Swiss roll to like the next layer outward. So what do we do in the ISOMAP algorithm? I construct that graph. I compute distances between every pair of points, not in 3D here, but rather as shortest path distances along that graph. And then I use MDS on that matrix. And what do I get? Well, I get something that unrolls the Swiss roll, like on the right-hand side here, right? Which is exactly what we want. So when people talk about ISOMAP, essentially all it is it's just like a Band-Aid put on top of an extrinsic technique, right? Where my Band-Aid is to construct a graph on my data and use distances along that graph, rather than using distances in the original space. Yeah? This is sort of facilitated. It turns out that pairwise distance in a graph is like one of these classic problems that you learn about in your algorithms class. There are many different algorithms for it. There's one that fits in about 4 lines of code called Floyd-Warshall, right, where you just keep taking triplets of points and fixing the triangle inequality. But in any event, the basic takeaway here is that this is a very straightforward technique in practice, and we'll unroll the Swiss roll just like you might want. There are many variations of this thing. One thing you might ask is, distances in a graph is kind of an expensive thing to compute. So some people will ask questions like, maybe I choose a few random landmarks inside of my graph, and I compute the distance from that point to all the others. So not like the n squared distances, but like k times n, where k is much smaller than n. And it turns out that you can do that, and there's a variant called landmark ISOMAP. Maybe we'll skip that for now. Okay, so essentially, hopefully the takeaway that you guys have so far, even if some of the math details went by a little quickly, is that there's many different techniques out there for embedding, and they're all kind of similarly behaved, A, and B, they all are not so difficult to implement. So it tends to be that the challenge for these techniques is deriving them mathematically, and the actual coding is really not so hard. And the convenient thing is that if you're using Python, MATLAB, R, any of your favorite data science, machine learning tools, they tend to be just built in. So it's a one-line call. So from a practical perspective, what do I advise when it comes to actually choosing one of these things is, try 10 of them, see which one works best for your data, and then go with it, right? Like these are not so complicated to try. This is very different from like training a deep network or something that takes a lot of time and expertise to get right. There are many other algorithms out there, incidentally. Another one is locally linear embedding, or LLE. This is very similar to the ISOMAP algorithm, where you, again, construct your k-nearest neighbor graph, but in this case, you find an embedding where, like, I noticed that every point is sort of the weighted average of its k-nearest neighbors, kind of roughly. So then I try to find an embedding that preserves that relationship. This is a little bit different from preserving the pairwise distances in the k-nearest neighbor graph. And there are advantages and disadvantages to both. So here's a nice figure where we've compared these two algorithms. And there's two different data sets. Here's the Swiss roll data set on the left-hand side. On the right-hand side, I think it's really cute. They call this the Swiss hole data set. So if you look very closely at that Swiss roll, you'll notice that somebody punched a hole out of the side. So this is a great comparison for ISOMAP versus LLE. So remember, what does ISOMAP do? It constructs a k-nearest neighbor graph. It computes distances in that graph, and then it uses those and tries to embed them. Now in the Swiss hole data set, kind of a weird thing happens, right? So here's my object unrolled. Now we've punched a hole in it, like that. What is the distance in the k-nearest neighbor graph between this point and that point? Well, there's no longer anything in this hole, right? There's no data points to follow, right? So the distance is actually kind of large, right? It's like that. So what's going to happen if I try to embed this data using the ISOMAP algorithm? Well, it's going to say, I want these points actually to move apart from each other because their distance is larger in that graph setup that I had, right? So the embedding that I'll get looks something like this, where I've taken that hole and I've expanded it. And indeed, you can see on the right-hand side here, that's exactly what happens when you use ISOMAP. The LLE algorithm is just trying to find relationships between points and their neighbors, so you don't actually ever compute the distance from these 2 points together, and so the embedding that you get is like the bottom row, the bottom right in this image here. So hopefully that distinction makes some sense. Okay, fabulous. There's one additional embedding algorithm we should talk about very, very briefly, and then we'll talk about some interesting extensions, machine learning techniques, and so on. And I'm just going to mention it by name now, and then 2 days from now, we're going to talk about all things Laplacian operator in geometry. The Laplacian operator is a very popular object in semi-supervised learning and some other places, and this is a better fit for that discussion. But there's one other technique out there called diffusion maps. It's just another kind of piece of code that you can code up. It's very simple. So in practice, diffusion maps is really easy. You have these points you want to embed. Now you compute e to the minus distance between every pair of these points, and you use the dominant eigenvectors of that matrix as your embedding. And we'll see that there's a sort of a very deep reason why that's a reasonable thing to do, but we're going to defer that to Wednesday. Okay. Right. So the big takeaway here is there's a big zoo of embedding techniques out there. They all have different theoretical properties and they work for different types of data. If you're in this sort of exploratory phase of data analysis where you're not sure what works best, one thing you could do is try these different techniques, see which ones tends to be successful for the data that you have. And this gives you some clue as to the structure that's hiding in the data set you're trying to analyze. So to conclude for today, I thought we'd spend 10 minutes discussing different kind of interesting distance matrix related problems that are in the machine learning world that are worth calling out. And then we'll conclude our discussion of distance techniques. By the way, to give you a preview of tomorrow and Wednesday, tomorrow we will talk about manifold optimization tools. So there's a very popular piece of software out there called ManOps, which is useful in a lot of, especially computer vision scenarios where you have optimization variables that are like rotation matrices and like how to cope with that kind of space. And then on Wednesday, we'll talk about semi-supervised problems and Laplacian operators. So to conclude our discussion of distance metrics, I thought I'd call out some other kind of interesting learning problems that appear. One of them is something called the metric nearness problem. So remember I told you that not all distance metrics are embeddable. It's also the case that sometimes you're given a bunch of approximate relationships and you suspect that they should have a distance structure, but you didn't quite get it. So for instance, maybe I run a big survey of everybody in this classroom and I ask like, do you like apples or oranges better? And then do you like, oranges or bananas better? And then apples and bananas and so on, and every single pair of these things, right? Then maybe there's a triangle inequality structure that's hiding there, right? Because if I like apples better than oranges and oranges better than bananas, then, I suspect them to, apples and bananas to be even farther apart. But just by virtue of being inconsistent humans, that doesn't always happen when you compute your data in practice. And so one thing you can do is solve something called the metric nearness problem. It is essentially intended to take a distance matrix and find the closest approximation of that thing that actually satisfies the triangle inequality. So this can be useful sometimes as sort of a pre-processing step for your embedding problem, for instance. Another thing you can do, sort of similar to the Netflix problem that people talk about, is something called distance matrix completion. Right? So maybe I have a couple distances between points, but I don't have all of them, and I'm trying to complete it. Notice that the constraint that a matrix satisfies the triangle inequality is a bunch of linear inequality constraints. It's actually a convex constraint. Right? And so it's not all that unreasonable that you can formulate lots of different problems that involve essentially trying to complete a matrix where some entries are missing, but I know that those entries come from triangle inequality style relationship. I think we don't have enough time to cover maximum variance unfolding, so maybe we'll skip that. And then finally, of course, it's worth noting that these days when we talk about embedding problems, oftentimes the embedding is really like the last layer of a neural network. And some of the most popular techniques that we have in the last couple of years basically take all of those objective functions that we've already talked about, right, like stress majorization and MDS, but essentially, rather than cooking up these really clever bespoke optimization algorithms that try to minimize these things in practice, they just use stochastic gradient descent. And what that allows you to do is to think of your embedding as the output of a neural network, which is useful in a lot of different contexts. So remember, at the beginning of our discussion today, I mentioned this word-to-vec algorithm. If you take a look at the research paper that's describing word-to-vec, it's just the same optimization objective as what we talked about before, the SMACOF technique, but it's hiding inside of sort of the last output of this skip-gram architecture, which is a particular neural net architecture designed to work in natural language processing. Right, so the basic takeaway here is that this is not a relevant tool, even though these days somehow deep learning is dominating the machine learning world. But perhaps the more important takeaway for a lot of these algorithms nowadays is the objective function rather than the very clever technique that we have for optimizing, right? Like all the derivation that we did on the screen earlier is interesting and totally relevant to these embedding problems where you just have a bunch of distances and you want to embed. But if you're solving problems in metric learning and so on where, yeah, you want to find an embedding, but you're getting it from an indirect signal about your data, the objective function might still be useful even if the optimization technique no longer is relevant. Now, of course, in an hour-and-a-half lecture, this is just the tip of the iceberg, and there are many different questions that we should think about. We've touched on a few interesting computational problems, right? Everything from, is my data embeddable? So oftentimes you read about these trendy research areas like manifold learning, right, where you draw these beautiful schematic diagrams of, somehow your high-dimensional, medical data is somehow sitting on a low-dimensional submanifold of R to the 200. If only you could find it, and then your inference procedure succeeds. But then when you actually look at these manifold learning algorithms, what do? Well, they sort of have these crazy parameters, like what is the dimensionality of your data? What is the intrinsic dimensionality of your data? What is the extrinsic dimensionality of your data? Are these easy parameters to compute in practice? Probably not, right? I mean, like, who knows what the intrinsic dimensionality of my blood pressure, height, and weight survey data is, right? And so one of the biggest open challenges is sort of reliably detecting that structure. In other words, asking the question is, are these tools relevant before I start to use them? Yeah, so there's some heuristic techniques for that, but I think the most basic version of what sometimes is called the manifold hypothesis is often quite difficult to test. There are other interesting computational problems that might link to things that you've learned about in computer science theory class. Right? So for instance, you could ask, if I have two different metric matrices, are these actually isometric? So is there a permutation of the rows and columns of one metric so that it kind of resembles the other one? This is sometimes known as the quadratic assignment problem, and it is sort of classically NP-hard problem. But it doesn't mean that we shouldn't solve it in practice. Right? So for instance, oftentimes in transfer learning, your goal is you have two data sets and maybe you know a lot more about one data set than another. So a very typical thing to do would be to try to find a matching from the first data set into the second so that I can kind of take the information that I know about one and push it forward into the other. So what's important to know here is that it's sort of a very classic instance of a computationally difficult problem, But that doesn't stop people from solving it in practice, right? So for instance, in optimal transport, like what you heard about from Marco this morning, if you search for the Gromov-Wasserstein distance between metric spaces, it's really just an instance of quadratic assignment problem, but it's also a very successful model that it's been applied to natural language processing, transfer learning, and many other tasks. And of course, you can look into all kinds of other crazy questions. So for instance, one thing that's quite popular right now in the neural network literature is to say, well, why does the output of my neural network have to be Euclidean? Like maybe I should output into a hyperbolic space or into a sphere or something else. And it turns out that, remember, hopefully I convinced you guys that not every space embeds particularly well into Euclidean space. So maybe I should be coming up with neural networks that embed into other areas. So a very classic example of that, just to draw a little bit of a schematic. Oh no, I'm on page 10. Oh wait, I have an idea. If I shrink, oh, the screen doesn't work, okay. So if I take this, we're gonna do this in a geometry fashion. Yeah, so if I, nope, didn't work. All right, well, I thought I was being clever. We'll do the opposite. Okay, now we have a fresh page. Right, so let's say that I have tree structured data. So this happens often in biology, right? So I have, a node, and it has children, like that. There's a big issue in this type of data, which is that there's a lot more stuff here than there is here. This is a very classic type of data that does not embed well into Euclidean space because the expansion factor is quite large. And so there's another type of object that has a similar structure, which is a potato chip. Yeah? So potato chips are hyperbolic, at least the ideal potato chip, geometrically speaking. Has a structure that looks kind of like that, right? When you have a potato chip, it tends to be curved. Now, what's the interesting geometry of a potato chip? There's a lot of radius relative to the amount of area in a potato chip. That makes sense? So if I draw concentric circles on a potato chip, I encourage you to all do this at home. What you'll see is that for the amount of area enclosed, the amount of radius that you have is much larger than just flat on the plane. And that sort of has a similar structure to what you see in this tree structured data. Right, so currently, I think the state-of-the-art machine learning, kind of deep learning tools for dealing with these sort of taxonomy-style problems in biology actually doesn't embed into Euclidean space. These deep networks don't output numbers, but rather actually output points in the Poincare disk, which is a negatively curved space. And the reason is that I'd like to fit, I'd like to embed my tree into a space where I have this nice branching factor like that. In order to do that, I need more radius out here than would be available to me on the plane. So it's a really clever trick. It's essentially just geometric in nature. And so finally, I should point out that almost all of these embedding problems are hard, incidentally, computationally speaking. So for instance, even if my data does embed well, one thing to know is that most of the techniques that we've talked about here are non-convex. They depend on your initial guess, all that good stuff. And so you have to be a little bit careful using these things in practice. So in any event, I think that was a far too fast-moving introduction to embedding problems, algorithms, some of the theory that's sitting underneath these things. But as your sort of token geometry theory person here this week, it's my goal to at least expose you to some of the interesting challenges that we have in this area and get you thinking about the kind of things that can go wrong if you use these tools without using them carefully.